That's done. Let's see the next item of business. So all right, so now we are done with discussing just these, individual combinations. What I'd like to do now is do a couple of, mixed resistor problems. Okay, as I said, it's not like we always have just a series combination or just a parallel combination. We can have, you know uh, mixed, mixed combination, you could say. So let's see. First one I'd like to do is a very simple one actually. Suppose, say, if you have, oops, if you have 4 ohms. So all right, so, and I'll just draw a cell here, although it's not really necessary. So for this one, I'll again just find the current, like we have been doing. So 4 ohms, 2 ohms, 2 ohms, and let's say that this is 15 volts. uh, Alright, so here, this is the current. Okay, so let's first find, well, we have, um, here you can see there's parallel combination, right? Just this much, not the whole thing. So just this much, this is a parallel combination, and this resistance is going to be, let's write as R sub P. It's going to be 2 inverse plus 2 inverse and the whole thing inverse. Alright, so that's, you can check it out. It's going to be 1 ohm. Okay, it's going to be 1 ohm. Half plus half is 1, and then half, you take the reciprocal, still going to be 1. Alright, and interestingly, this is exactly half of what this was, and both of these are equal. Okay, 2 ohms. So there's actually something, there's something interesting here, just a bit. But anyways, I'll discuss about that later. Nothing to worry too much about. But anyways, so this is 1 ohm. All right, just this much. Now we have, um, 4 ohm. Okay, so if I consider just the resistances here, I have 4 ohms. All right, and this is in series with this 1 ohm resistor. All right, this 1 ohm resistor, right, which you just found. Okay, now, and these two are in series, so they add up, so it's 1 plus 4, that will be equal to 5 ohms. So the equivalent resistor of this whole combination, this whole mixed combination, is going to be just one 5 ohm resistor. All right, so, and this is connected across a 15 volt cell. Okay, so the current here is going to be, 15 over 5, which is 3 amps. So I is going to be 15 over 5, so which is 3 amps, right? All right, so let's do another example, slightly more difficult one. Let's see. Okay, so here I have this combination, and as I said, it's not like we need a cell every time. Let's just, the question here is just to find the, the equivalent resistance. All right, so first off, we see this, we're going to work from big to, small to big. Okay, small to big. So first, here, this is a parallel combination. All right, so we get, for this one, if I want to find the resistance here, so for the equivalent resistance of that combination is, so the, yeah, it's 42 and 75, right? So 42 inverse plus 75 inverse, whole thing, take the reciprocal. So you have 350 by 13, right? So 350 by 13. Okay, so here this is equal to 350 by 13. right? So what I have is, if if I do this, if I turn this into the equivalent resistor, I have, so everything else is the same except this is just one resistor. And well, we can do a few more things, you know, these well, I'll just hold off on that one now. Same thing really, if I add three of them together, and we have for 14.5 here, right? and so this is another resistor. Okay, so and the values are here, it's 350 by 13, 350 by 13, and I'm going to omit, you know, writing ohms for all of these, because as you know, all of these are in ohms, as you can see. So 33, 61, 14.5, 14.5, and 25. All right, so next thing, we can see that all of these three are in series, right? These three are in series, so they add up. So their sum, the equivalent resistance here, is 33 plus 61. That's our previous answer. So this is okay, 1572 by 13. 1572 by 13. So if I turn this to the equivalent resistance, I have, so one resistor, which is 151,572 over 13, that's that value, and this is connected in parallel, as you can see, to a 14.5 ohm resistor. Okay. Well, I just said I would omit ohms, but anyways, wrote that out of habit, and this is 25. All right, now again, these two are in parallel, right? These two are in parallel, right? So the equivalent resistance here is going to be, it's going to be this inverse plus this inverse, and then the whole thing inverse. So we have, let's see, so our previous answer, take the reciprocal of that, plus 14.5, take the reciprocal of that, then take the reciprocal of the whole thing, we get okay, so seems like the calculator isn't able to give us a fractional, you know, exact answer anymore. So this is 12.95, let's see, 12.95. Right, so we have 12.95, 12.95, and connected with 25. All right, so connected with 25. All right, so well, these two are in series, so the equivalent resistance of that whole combination is going to be just this plus 25. Okay, this plus 25. Well, we don't really need the calculator for that. So 3 and, so yeah, 37, 37, 37.95, 37.95 ohms. So this is my equivalent resistance for that whole, you know, large combination. We just found this out. It's pretty neat that you could simplify something like this to just you know, this is basically a single resistor, right? A single resistor that has this value, right? 37.95 ohms. All right, so we were simply be able to simplify this to something like this. All right, so that's neat. Okay, just one last thing, let's just try it out. Okay, is this is just something extra. Suppose, say, I had a switch in parallel with you know, all of this. Okay, and this is currently switched off or open. So what would be the equivalent resistance when this is open, okay, or switched off, and what would be when I close it, okay, or when I turn it on? So for both cases, I'd like to find the equivalent resistance. Well, when it's open, like we discussed in the last video, this doesn't really affect you know, anything, to be honest. You know, having an open circuit, okay, or a gap, you know, an infinite resistance in parallel with you know, another you know, this whole thing is basically another resistor, it wouldn't affect anything, okay, if you have an open circuit in parallel. All right. So and you can, I'd really encourage you to do one thing. Take your parallel resistance formula, okay, take your parallel resistance formula and see why it doesn't change anything to have, to have an open circuit. Why it doesn't change anything? Use the fact that the, resistance of an open circuit is basically infinite. All right. So if that's the case, and if that's the case, then the equivalent resistance is going to be the same as before. Okay, so it's the same as before. But what happens if I close this? What happens if I turn the switch on? If I close this, so then as we discussed, oops, okay, so then as we discussed, basically we have uh, one some resistance. To be honest, we not really even need to find this. Okay, if you encounter this question where you have a short circuit in parallel with some other resistance, okay, you can basically just say, okay, so this is well, you wouldn't need to simplify this. You can just say, okay, this is going to be some resistance. Okay, I'd have some equivalent resistance, and this is in parallel with short circuit. Okay, just zero resistance thin wire, and as we saw, this would basically make the resistance zero. Okay, no matter how many resistance you have in parallel with a short circuit, your resistance is always your equivalent resistance is going to be zero. All right, so that's basically how you'd find the answer, and we are done. Just one more thing, which I don't want to extend this for too long, but I did say I'd show you something regarding this, where we had 2 ohms in parallel and we got half the answer. This is not actually exactly a coincidence. There's something interesting. If you have, like, let's see, resistance R, okay, so, and like this, let's see. So all of these, suppose they have the same value. So for series combination, okay, a series combination where all of them have the same value, this one's not really that important. It's pretty obvious that if you have n of them, okay, if you have n of them, you just add all of them. R plus R plus R. So this is going to be your equivalent resistance. R plus R plus R. You do this n times, okay. You do this n times, so there are n of these, right? So there are n of these, okay. So your answer is just going to be n into r, okay, n into r. So that's for series. And for parallel, interestingly, if you have n resistors of the same value in parallel, okay, so this is 1, this is 2. I'm just drawing the diagram for visualizing. It's not really that important to draw this. So this is the third one, and you'd have, let's say, n of these in total, okay. All right, so let's see, this is R, this is R, same as before, let's say. So n resistors with the same resistance in parallel. Now what does our parallel resistance formula tell us? That this is R sub equivalent, the inverse of that, the reciprocal. So 1 by R, again same process as before, except the reciprocals here, but again those are added n times, okay. Those are added n times. So you'd have n, here you'd have n into 1 by R, okay. And when you take the reciprocal of that, okay, to find the equivalent resistance, what you get is the equivalent resistance is equal to R divided by N, okay. I'll do this in a different color. This is R divided by N. So just something interesting, and this kind of following that trend that series and parallel resistors have properties which are flipped around, or opposite, you could say. Here, if you have n resistors, the same value, they're in series. It's you multiply, you scale up your the resistance of the one resistor, okay, by your number of resistors. Okay, and here you divide. Okay, you divide the resistance of one resistor by your total number of resistors. So just another thing, just something that's interesting to see. And to be honest, like when you just keep dealing with these mixed resistor problems, you actually instinctually get the habit of using this one. Okay, this one's pretty obvious, but you also instinctually get the habit of using this one. Just something convenient when you have cases like this, or when you have, suppose, say, 6 ohms, 6 ohms, um, you know and 6 ohms, let's say. Okay, 6 ohms, 6 ohms here, 6 ohms here, 6 ohms here. Okay, so like obviously, first time I was learning all these, I just took out my formula, did the calculation, and then I'd get my answer. But as I kept doing these, I'd just instinctually get the habit of, okay, so look, three resistors, same resistance, they're in parallel. So what I'd get is, the value of 1 divided by, there are 3, so you get 2 ohms. 2 ohms, that's my equivalent resistance. Okay, that's my equivalent resistance. So anyways, that's all. I really don't want to extend this more than necessary. If you have any suggestions, please do leave it in the comments. If you noticed any issues or mistakes in this video, also please do tell me about it. And especially if you appreciated this video and found it helpful, please do leave a like, subscribe, and please do continue supporting my channel. I hope I can deliver much better content. And yeah, another disclaimer: the next video, hopefully I deal with more complicated series and parallel combinations, okay, which are a bit harder to recognize, you could say. So that's for the next video, for those who are interested. And yeah, study smart.